Dear colleagues, dear students, I have the great pleasure today to start this new cycle of sessions of the International Seminar on Social Media Discourse Analysis for the academic year 2025-2026. Let me remind you that this seminar is convened by three universities belonging to the Civis Alliance: Aix-Marseille Université, Université Libre de Bruxelles, and Stockholm University. And it is also supported by Maison Française d'Oxford. Once again, I would like to thank my laboratory, l'ERMA, which contributes to the funding of the seminar. I'm very glad to welcome my colleague and friend, Professor Bernie Hogan. I will give you some information about the format of the session. First, we will listen to our keynote speaker, and after his paper, you will be able to react and ask him questions. During the session, I will ask you to mute your microphones during the talk. You could switch them on again if you want to ask questions later on. You will be able to ask questions either by raising your virtual hands or by typing your questions in the chat window. It is my great pleasure to introduce our speaker, Professor Bernie Hogan. He is an associate professor, a senior research fellow at the Oxford Internet Institute, and a research associate at the Department of Sociology at the University of Oxford. He is the author or co-author of dozens of peer-reviewed papers on online culture and social networks. Hogan's theoretical work was among the first to identify the role of the social media platform as curator and to distinguish certain social media as the real name web. His practical work has shown how network visualizations can reveal new information to individuals from their social media data. He believes that the way networked information comes us in feeds is akin to being given a route through social space. His book, From Social Science to Data Science, was published in 2022. We know that generative AI systems use inference in order to provide responses to users. A multimodal analysis will help them to produce answers. Some of them sound irrelevant, as these systems may confuse dates, facts, and sometimes generate untoward assumptions. Actually, we should question what an appropriate assumption is, and we should assess the different biases that could emerge in the answers provided by AI systems. This is precisely what Professor Hogan will tackle in his talk today. The title of his paper is The Autoencoder's Dilemma: Semantic Superposition and Learning from Machine Learning. Bernie, we're listening to you.
Oh, thank you very much, Gregor. That's it's a real pleasure to be here. Oh, I have an echo, by the way. Let's see if that settles down. Okay, we're good. So, yeah, it's a real pleasure to be here today. I am, uh, I'm always in motion in many ways. My work tends to evolve over time, and my work has become increasingly focused on artificial intelligence, but not in the sense of, oh, there is this AI thing out there. How do we use it? What's it good for? But rather, how can it help us understand meaning? How can it help us understand what it means to encode meaning, what it means to make meaning available to other people? We can't say that the artificial intelligence systems themselves uh, have have an internal representation of meaning that's similar to people. And I certainly am not here to make that claim. But I am here to make a claim that there are trade-offs in meaning which are experienced similarly for machine systems and for human systems. And those trade-offs reveal that the words that we use, the way that we use them, involves multiple meanings. It's certainly not a new concept, but that those multiple meanings are a really important part of how we understand how machine learning systems work, what the implications of those systems are, and actually what the implications are for meaning more broadly. What is it? How do we understand what it is to convey meaning to someone else? There's some political consequences to this as well. If the way that I can express myself is limited to certain frames of reference, if we can really only talk about things in some way, then it makes it hard for me to send a new idea, a creative idea to someone else. We see the work of great poets and authors in history have really been able to capture and transmit various complex and subtle ideas. And one might worry, is that complexity being reduced by artificial intelligence systems? Is our ability to express ourselves being steered in a particular way? And what does it mean to steer a meaning in one way or another? So I've been thinking about these topics for a long time. And my history for this actually starts in social network analysis. But I don't want to say it's culminated, but I will say it's not like this is the peak or the end or anything, but I will say it's kind of built towards now this work that I'm doing in artificial intelligence, some of which is of a theoretical nature. And I'm hoping that the theoretical ideas I communicate today will be useful to people. We don't normally think about theory when it comes to machine learning and artificial intelligence, at least not directly. We think about its implications for social theory or theories of expressing ourselves. But what is a theory of machine learning that can help us navigate this? And when we find that machine learning theory, well, how far out does it generalize? How much else can we say about the world through that? So I use a frame here called autoencoding and encoding, and I find them to be dilemmas or trade-offs. So what we'll go through today is a paper that I've submitted. It's in review at present, and try to communicate some of those dilemmas or trade-offs about meaning that we've learned through machine learning, and see how we can make use of that in socially meaningful ways. So I'm going to share my screen here. That means it's going to be a bit tricky to see if anyone's got the cameras on and stuff like that. But at the end, I'm happy to take questions. Now, Gregoire, for the rest of this session, my understanding is this is a 2-hour session. Is that correct?
Yes, it is.
And so we would probably want this to wrap up what I'm saying around 5 o'clock. I have all kinds of extra fun things to show or whatever if we end up a bit quick, but I'll try to leave time at the end. So please think about a question, writing it down, and you can think a bit more broadly than this if you like. I do have a pretty broad sense of machine learning technologies based on the fortunate position that I have at the Oxford Internet Institute. At that institute, we let's see if I'm sharing the right one. Here we are. There we go. Yeah, so at that institute, uh, this is oh, and you're seeing the wrong screen, I imagine. Let me just do that again, and we'll see if we can share the correct one. Actually, to confirm, do you just see the title slide now, or do you see the title slide and a bunch of other slides?
I can see the other slides,
Yeah, that's what
the
I
next
thought.
slide.
Yeah, that's what I thought. So give me 1 second, and I'll swap that around so that we are sharing the right screen. Okay, desktop 2. We'll share that. We'll place that up there. All right. Yeah, so this is the autoencoder's dilemma. Now, I've given it a different subtitle. It's basically the same talk I'll give in a couple ways, but I will say a lot of this is really new to this talk now. That's because I wanted to see if I can express those ideas more effectively. So here we say, can I say what I mean? Can I mean what I say? And those are two really important challenges for the understanding discourse, the relationship between discourse and ideology. If an ideology or some sort of set of values even is what I mean, how do I express them in a way that makes my ideologies coherent to someone else? Now, this actually didn't start in some respects with with language for me. In fact, it started with social networks. And we might think of it started with the epistemology of social networks. How do we come to know what is a set of connections between people? So we have here in the background a series of what's been called egocentric networks. These are networks of individuals and the connections between those individuals. These are all Facebook networks. Now, we're not going to focus on the implications of these networks. I won't say too much about them. They're in a paper of mine with a large number of co-authors by Elizabeth McConnell. It's a pity I don't have the reference there, but it's called Everyone Puts Their Whole Life on Facebook. And it's about the identity of LGBTQ plus individuals. And I'm saying that specifically LGBTQ plus because I'm gonna come back to that phrase later on. Um, the paper's findings were what they are, but I think what's important about this is that the way that we were able to get these networks was through Facebook. And I'm not saying that because you can do that anymore. You cannot. You cannot. But the point is that the networks themselves are based on friendship relations that are negotiated between two people. Do you want to be my friend? Yes. Okay. Now we're friends. And that friendship is shared everywhere on Facebook. If I'm friends with someone and a third party knows both of us, that third party will see either we are or are not friends on Facebook. That's that there's no kind of ambiguity about whether people are connected or not in these networks. But on the other hand, if if these networks are Facebook friendships, that's not the same thing as a real friendship. And we know that. We know people befriend each other. They signify a friendship on Facebook for all kinds of reasons. It might be social pressure because our friends know each other. It's not necessarily a view of the social map that people have. We might consider it a cognitive map of who is in their world and how those pieces fit together. So that's actually what I've been doing in my a lot of my practical work, and that says, who's in your social network, and it might depend on the question. And so this is an early example of the program Network Canvas. That program's really come a long way. In the early days, what we had is it's like an interview. You have two people, one sort of, adding names, and then they're moving them around on the screen and saying, here is my network. More recently, and if I can, let's see if I can swap that screen over. Um, okay, yes, more recently. We've been working on this program, Network Canvas, right here. This is at networkcanvas.com. Apologies if it's a bit small. It's not really meant to be an advertisement. But the point is that what we're doing is we're getting things from a person's perspective. And if all of these people here were in someone else's network, that other person might draw some lines differently. They might add some people differently. Everyone will have their own idea about who's connected among all these friendships. So when I ask the question, are these two people friends? Well, the answer is going to depend on who you ask. Uh, you might ask me, and I say, yeah, they seem like friends. I've seen them talking at the office. Maybe I'm just making a guess. Whereas you might ask one of the two people and say, are you friends with the other person? And they go, not really friends. We were acquaintances. We know each other, but we're not friends. So the word friend becomes this kind of contested space where it could have multiple meanings. And how do we unpack what those meanings are? How do we understand that? Well, we can take a page from machine learning. And for the rest of the presentation, I really just want to unpack these concepts. I'm taking it a bit slow here because I want to make sure I can get as much information about these concepts out. But I'm more than welcome to take questions on this if people are not sure. And I am going to have to gloss over some of the technical stuff, but I don't want it to be seen as to intimidate you or to show you that oh, you really need to know the math. I'm happy to unpack some of the more technical stuff if it helps your comprehension later on. But here's the two trade-offs. The first one is called the bias variance trade-off, and the second one's called the curse of dimensionality. So the bias variance trade-off is the idea that you cannot decrease the bias and the variance at the same time. And so what do we mean by bias and variance? Bias, you can be more specific, but you might miss the target. That's to say, I can be really particular about a thing, but what happens is as I become more particular, it's harder to hit a big target. And it's harder to say this is exactly, um, I could say this is a very clear statement, but I cannot be sure that that clear statement covers everything. I could say, well, um, let's make a statement that's more elaborate. We'll say a friend equals this, or it could equal that, or a friend could equal this, and so forth. And then that's more vague. Then what a friend is, it's a more generalized idea. Um, and the problem is that if you have too much variance, you may fail to convey information. And so we have this, we can see this in the notion of a friend, where I could, for example, say a friend means exactly this, and then we'll have those. But if that meaning doesn't overlap with a bunch of other meanings, then we got trouble. We got bias, and we got what we would call the wrong kind of bias. So a Facebook friendship would be an example of some biased data. And that doesn't mean that it's wrong per se. It means that it's very precise. It's a very specific kind of thing. What does it really mean? It means someone said a Facebook request, someone else said, yes, I agree. That's what it means, practically. What do we think that it means? Well, it could mean that we're friends with each other. It could mean we're, interested in learning about each other. It could mean someone's a fan of someone. What happens is as soon as we get really precise, the friendship equals I ask, you agree, we start absorbing a bunch of variance. And so that the meaning itself ends up being really ambiguous. So we'll look through some examples of the bias variance trade-off. A lot of pictures in here. I like to use pictures where I can, and we'll see how that relates to meaning spaces. The second key trade-off is a thing called the curse of dimensionality. And that's when you add features to your model, you make it more sparse. So imagine instead of a Facebook friend, we had like 6 classes or maybe 8 classes of relation on Facebook. And we would say, well, now we have one for a friend, we have one for an acquaintance, we have one for people I know from work. We can have all these different kinds of relations that are in there. But as soon as we do that, it's going to make our model larger, but it's also going to make it more sparse because instead of everyone is a friend, now we have only a couple people in the work group, a couple people in the family group, a couple people in this group and stuff. And so that makes it harder for us to make a good prediction about what's going on. It's a lot easier when we have a very simple model, true or false, left or right. But again, when we do that, we're being biased. And so we're absorbing lots of variance. We could say, no, 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 we'll use lots of categories, get all the variance. But then it's hard to get the information from them. It's hard to think about how these things relate. So these two trade-offs are, in technical terms, they're kind of non-negotiable. They're not things that we have a solution towards in a kind of perfect sense. Instead, they're things where we have to absorb those trade-offs, absorb the trade-offs in meaning. So let's have a look at some implications. And we're going to start off and say that the bias variance trade-off is related to autoencoding. Now, what is autoencoding? In a formal sense in machine learning, what it is to decompose some object, and we can take a picture here, into a set of subspaces. And the picture then has some new data, new information in those subspaces. Now, this is a schema, but we're going to see some actual autoencoded stuff in a bit. This is a stylized set of images. So instead of having one image, you might have 3 smaller images that each sort of pull at different things in the image. Now, in this case, it's pretty much the same image, and you don't really get a feel for what's being compressed in there because this is not an actual autoencoding. If you see the little stars in the corner, these were done by Gemini. They were meant to kind of convey in a stylized sense what happens in autoencoding. We take something and then we, filter it into these smaller subspaces. And the idea is that the spaces that we filter in are smaller, but they each have different bits of information together. And then we can reconstruct the image from this smaller space. But we can also learn things about the world in these smaller spaces. So, how would we do that technically? Well, that involves the use of a thing called an eigenvector. Now, eigen is a German word, and in this sense, it means own or self or mine. Uh, and so, an eigenvector is like a my vector, but it's not really my vector, it's the data's vector. So, if we have here a series of points. These are dots. These are distributions. So variable A is one distribution and variable B might be a different distribution. And so what we see here is that it looks like there's a shape, doesn't there? It looks like there's a pattern. They kind of like all of them kind of fall down on an angle. So we can describe, say, one line to say what's the best line we can draw through this that is going to minimize the distance of the points to that line. And so some people see this in a thing called linear regression. This is a slightly different way to do it. But you'll see this is our first eigenvector right here, what we'd call a principal eigenvector or principal component or leading eigenvector, I suppose. And what it's doing is it's organizing the data along this axis right here. So it's not like x, y. Now we're saying what would be the axis that's like closest to all the points? How can we find what that is? Now, what that does is that says, well, if we just have this one axis that shows all the points, or is closely aligned with all the points, then it's a simple measure that we can use to characterize this much more complicated space. We can just turn it into that one line. We can say everybody kind of falls on that one line. Now, the interesting thing about eigenvectors is that there's not one of them. There's as many as you have rows or columns in your data. Well, closely. It's actually the minimum of rows or columns minus one. And then you take all of those, you could build back all your data. But the good thing is that the eigenvectors aren't equally weighted. The first one counts for a lot. The first one in this case really is just the line through the data, just like what we see. The second one is going to be what we say is orthogonal to that. And then maybe the third one would be orthogonal to that. And we just keep slicing them up. And they just get smaller and smaller on their influence. The main one that we see here is the main eigenvector that gives us the most information. And so that's something that we would want to make use of. So now we can use eigenvectors to decompose a lot of spaces. So here, have a look at a thing that's been around for a few years called eigenfaces. And this is something that's done in machine learning and facial detection and these sorts of tasks, where you have an eigenvector that says, here's where all the faces differ the most. So where are you in relation to that first eigenvector? And here's another way where faces differ. And here's another way that faces differ. And so when you stitch all of these faces together, you get a kind of average or very generalized face. But when you weight it before you stitch them together, then you get something that looks like a real face or a familiar face. And so here's an example of a face that was trained, and you can see how it's decomposed into these different subspaces right here. So each subspace is a kind of like a coordinate system, but it's a simplified way of characterizing the image or characterizing any particular concept, if you will. So then we what we can see is, oh, and I don't know that it has the little number. Well, it has the numbers on the next one, but the thing is that this training face will have some value for eigenface one. It might be a bit above or below, maybe, and for number two and for number three, and then so we don't just add these eigenfaces together. What we do is we use them as a kind of coordinate space. Now let's see how that coordinate space might work. And this is really neat. This is decoding the thought vector. So if these are all vectors, then what we can see here is that this person, that's one eigenvector, And this is what they look like here at the end. You're not adding anything else. You're just taking the one image and go for it. And you can kind of see in the background these other faces. So now just watch what happens as we add those faces to this. Just you can see it's just changed. And so it's become kind of all of those faces squished together. And if we keep going, we can see what happens. We add the sunglasses vector there, and we got sunglasses or we don't. Just watch, there's the sunglasses, and they stay on as long as that sunglasses vector is in. Oh, the sunglass vector is gone. And then this person still has like a little bit of that hair right there. That seemed really informative and so forth. And, et cetera, et cetera. So these thought vectors help us appreciate that when we take a measurement for some meaningful thing, that measurement, we can think of that measurement not just as like, are you happy on a scale of 1 to 10, but it can characterize happiness in general or something else in general. And we can work with those vectors together to combine them and produce something that might be interesting or intelligible or new or novel or whatever. Now that decoding the thought vector, that's actually this is a web page. It's not an article in a sense, but the person who did this, Gabriel Go, this is one of the last things he did in like 2016 before he got hired at OpenAI. And ever since then, he has been at OpenAI, and you may have seen some of his technologies like DALI or Sora, which are ways in which we produce like lifelike images and things. But all of that kind of comes down to this idea that we can combine not like one eye here and one eye there, but that we can kind of layer these things together. And you see how we might layer them. And so we'll add the sunglasses again, and then we, take the sunglasses away or something. And so the layering is about how we compress this information. All right. So now let's return to the presentation. Okay. Do. Now, I want to contrast this with another idea because the autoencoder requires us to think about the notion of compression, the idea that we're getting the gist of something, and it's not what happens here. What we saw before were eigenfaces. These were these generalized structures that represent face characteristics, and people have a coordinate space in these face characteristics. But this right here is not what we do. This is not what humans do, and it's not what diffusion models do. But it is what Snapchat does. This is a face map. This is the 48 point face map. And so each one of these points would be mapped onto an image of a face. And then you can move the face and say, move the eyebrow up or make it the mouth smiley. You can put a mask on there. There was, maybe it's like a puppy dog ears or something. That stuff is not autoencoding. That's layering on a map. But what we don't need is kind of the gist of the person's face. We don't need a generalized appreciation of the face. We need a specific, here is the map, just layer things on the map. Now it's important because this one doesn't require any compression. It just requires us to put the points and then we can like layer something on. It's like stretching a map or stretching a mask over a face. But that's not how things work uh, when we're compressing data or when we're storing data in in our heads or in a large language model. So now this is all relatively visual. And I think the crowd here would be wondering, well, how does this relate to language? How does this relate to semantics? And so, well, there's a short answer and a long answer. I'll give you the short answer, and then hopefully we'll talk through the long answer. So the short answer is we need to understand what people mean under imperfect conditions. Uh, we're not going to see everybody's face fully clear in the same way. People may have a beard or shave or some makeup. It- People age over time. How are we going to know who is who? Well, the idea is we don't just map in a very literal sense. This is what this person looks like exactly. Instead, we map in a more general sense these auto-encoded ideas. Um, so how might we also think about this in relation to the bias variance trade-off? So I have here an artifact that I've produced using Claude AI. I do like using these artifacts. There's the link to it. I guess if you screenshot it, you can try it. I will have the slides distributed after this lecture, and it'll have those in there. You can play around with it yourself. And it's this little artifact right here. This is something I've built, and what we have here is a challenge for an autoencoder. We see here we have people, there's their blood pressure, there's their age, and we're wondering whether they are at risk for some sort of cardiac event. And so, what I've labeled here are some people who have had a cardiac event, and those would be in red. And then the people in green who have not had a cardiac event. And what might we say? We might want to say, well, if you're getting old and your blood pressure is high, then you're at risk of a cardiac event. But is that always true? Well, we have this green person right here. They didn't have a cardiac event or something. It's actually pretty grim if this was the real stats. These are fake numbers. Um, so now we can add another patient here. There's a healthy patient. We can add another healthy patient or add one down here. We can add an at-risk patient down here. But here's the problem. Can we split this data into just those who are at risk and those who are not at risk? Well, it's pretty hard, isn't it? The thing is, we can draw this line, this red versus green shows us a kind of guess at this. This would be how the bias and variance trade-off operate for each other. So what we have here, the bias is about how complicated that line is. Right now, it's a simple line. So now look what happens if we go down and we use this regularization parameters. Watch what's going to happen to the data. It's going to make it really wiggly and craggy and all sorts of things. And so you can see here, I suppose the colors are not super clear, but this line first starts off very straight. Like, well, first it says no one. The best thing to do is say that no one has a heart attack. That's the simplest way. We say, well, we want to do better than that. So then you get this line coming in. It says, well, let's cut the data here. And then if we if we increase that regularization parameter, instead of cutting along a line, we get this like really weird kind of loopy structure. There's a little blob in there for the ones that are red. And what happens is that what we're doing now is we're fitting kind of too much to a distribution. We are overfitting. Overfitting in a semantic sense is like being really tedious, really pedantic. I describe it using the phrase actually. If you overfit, it's like saying, actually, this is the case. Actually, that is the case. So I might say, and as the example I gave in the paper is, well, The Godfather is one of the best movies ever. And is it? I don't know. It's a pretty good movie, sure. An actually person would say, well, actually, someone in the Village Voice said that it was not a very good movie in 1972 in a review. So we cannot say that that movie is universally loved because it's not universally loved. There is at least one person who did not like it. And that's like, okay, that's a bit too tedious. That's what happens when someone is using too much variance. And that's what we see here. Someone's using too much variance. They're trying to cover all the little bases. But as what happens then when you try to cover all the little bases, you don't get a thing that you can generalize. Like, is this person right here a fluke? Is that an accident? How about that one? If we try to make something fit every possible single unique circumstance, then what we lose is the ability to communicate. Well, in general, blood pressure and age higher, not safe. You should, worry about your heart, that sort of thing. Now, in machine learning, we have metrics for this. We have things like a training set and a test set. So what we do is we classify some part of the data, and then we apply it to some other part. Now you'll notice here when I have the regularization parameter really low, our accuracy is, well, it's 50-50 because that means half of them are in, half of them are not in. So it's not very good. It's half the time we're wrong. And it's only two classes, so that we're not doing any better than random. So how do we do better than random in our training data? As I increase the regularization parameter, you see what happens here is we're bringing this forward, and so we see that little red line's like cutting things, and it increases the accuracy. So that's good. We're able to make a better prediction who's safe or who is at risk. And then we have these things down here, precision and recall. I'm going to talk more about them later. But let's just say that they're scores for how we pick up things in the data. All right, now, but just look down here. This is the test data. So if we fit on this data, this is what we learned from. And the thing is if we learn from it in too tedious a way, well, then in our test data, it's not going to work. So just notice down here, when our regularization parameter is low, just look at this. We got a line, it's kind of a straight line. Our accuracy is 0.84, our accuracy here is 0.8. So if we generalize, if we go to another data set, our accuracy is still pretty good, right on. But if we increase the accuracy, just look, it starts to lower. It gets unstable. And by this point, our accuracy in the training data is really high. We've definitely nailed our classification, but the problem was we didn't do any better on our test data. We failed to generalize. Our test data doesn't have these weird little wiggly bits right here and here. And so, yeah, we used a lot of variance. We made very specific discussions, very specific contour to this distribution, but we didn't generalize that distribution. On the other hand, if we make a simpler cut, it does generalize, but at the same time, maybe not as accurate. So what we want to do is we want to see how can we mean what we say and say what we mean. So that is, how can we make a distinction here that you'll get as well? That we won't just get in the training data in my head, you'll get in your head as well. I will generalize, we can communicate effectively. If I'm really too particular, that could be really accurate for me, but it actually might not generalize to you. It might not be something that's accurate to your perception or to your view of the world. What we cannot do is optimize both. We can't make a cut that's going to work really simply and a cut that's going to cover all the bases. We have to make some trade-offs one way or the other. Okay, so now let's return to the slides. Okay, so the long answer. These imperfect conditions, we saw that. There was some green and some red. They're all scattered together, mean that what we can do is we'll embed our ideas. In this case, it was the points, the green and red, in some general way. We'll say, what's the eigenvector? What's the general way to classify this data? And are there other ways to classify this data? Some general ideas. We're not going to say like the face map. The face map would be like saying there are some people who we will say that is definitely yes, definitely no. Instead, we have a world where things are a little more vague. Sometimes things turn out to be accurate, sometimes they don't. So we say here our predictions can be more accurate with a more complex model or more generalizable with a simpler model. So we want something that's both accurate and generalizable. That's our trade-off. And so why did I talk about those eigenvectors for like eigenfaces? Well, it's one of an ensemble of ways in which we try to characterize the data that makes it the most general with the least amount of detail. Any more detail, and you might be getting too specific. Any less detail, and you're not characterizing what you mean. All right, so that's just a general thing in machine learning, bias variance trade-off. Well, how does it apply to people? Well, here I draw upon the work of Fred Dretzka. And this is from a book that I really, really like. I only found it this year and I was thrilled to find it. It's very well cited in the philosophy of epistemology, but I didn't come across it until February. But it really, really works for me. The book starts off with a discussion of what is entropy. And because people don't necessarily know what entropy is, but they know that there's this thing called information, or there's a formula for information, Shannon information. And Dretske walks through this in like really useful detail. I won't go into all the detail, but the important thing is that what we normally think of information, we think of what's called structural information, something where there is a right answer or a wrong answer, and you either get it or you don't get it. Um, and so that is the world of the bit, 0 or 1. That is structural information. If I download a file from the internet, I don't get the eigenvector of that file. I don't get kind of a generalized version of that file. I either get the file or I get something that is corrupted, that is incorrect in some way. That's the world of structural information. We are just getting all of these structures, the ones and the zeros, no ambiguity. In this diagram, that represents this wedge right here, ISR, information sent that's been received. So if you're a receiver, you got to receive some information. What you get is IR, which is the information sent that's been received plus noise. So if I say, I went to the store yesterday, it doesn't sound very clear, does it? Right? It's like, what did I say? It's there was a lot of noise. If I said I went to the store yesterday, there's less noise. You probably are starting to get the message. And but if I said I went to the store yesterday, there was even less noise. Okay, sure. So therefore, the information sent is I went to the store yesterday. What does that mean? Which store? Do I normally go to the store? Is it my partner's job to go to the store? Does the store mean a club or a place called the store? Or does it actually mean like, a shop where any old shop I went to, a Tesco or a Carrefour or something to go buy things? All of that is unclear. So in the case of structural information, we don't care about that. So we're just saying the information sent that's received is the noise plus the stuff that's sent. But for semantic information, it's different. What gets sent is all of this right here. This, and what's this E stand for? Equivocation. The fact that the store could refer to a place called the store. There is, in fact, a place in Oxford that's called the store. It could mean that. It could mean a particular grocery store. It could mean something. How are we going to find out what that means? Well, the thing is that what I send, when I send the information, when I just say I went to the store, that's the information sent. So we're not just giving the information that gets received. We're also sending along all the equivocation, all the potential for multiple meanings, all the different ways that we could get this or not get this. Now reduce um, we can reduce channel noise. We can reduce it. We can say, could you say that more clearly? So what is that? I misheard what you said. Could you say that more clearly? That's reducing noise. But what it doesn't do is reduce ambiguity. I wouldn't say, can you see that more clearly or say that more clearly if I did not know which store. I would say, which store did you go to? But if I asked, if someone asked me to go to the store and and so my partner comes home and they're like, "Hi, how are you doing?" And I say, "I'm doing good." And then say, "Well, what did you do yesterday? How have you been? I haven't seen you since yesterday." He's like, "Well, I went to the store yesterday." "Oh, great. Did you get the stuff I asked about?" Right? So that person would have a context to de-equivocate the information. But if they did not have that context, then they would not have that same ability. They would have to make an inference. They would have to make a guess. So Why don't they just make the right guess? Well, that goes back to the precision and recall thing that I had mentioned. Why don't they make the right guess? Is because, well, some guesses are more general and they probably cover more space. I assume that you went to a place where you buy goods, right? That's a pretty general guess. Doesn't carry a lot of information. Or I could make a very precise guess. I could say, did you go to Tesco or Waitrose? But then in order to do that, I have to add in new information. So how do I figure out which is the likely way forward? I take the gist of this. I make auto-encoded impressions. I build myself a little model of the world where I make expectations for that. So if I'm talking to someone who's close to me, I might think, oh, they went to the store, I asked them to go, yada, yada. If it's someone who's not close to me, I don't have as clear a model. I can't make a precise statement. I don't have a good sense of it, but I still have some sense of it. Okay. So now it's important to think the implications of this are about are, well, first of all, are undermining some simple ideas about the world. The first simple idea is that learning is this process almost like building a bookshelf, where you read another book and then you put it on the bookshelf of your mind. And then you read another book and you put that one on the bookshelf of your mind. And at some point, because it's a bookshelf, it gets full. And so therefore, oh, I cannot put any more books on the bookshelf. That would be like saying, I cannot learn anymore. It's this cartoon here. Can I be excused? My brain is full. Now, it might be the case that you need time to process a concept. That's fair. But we wouldn't say that your brain is full. We wouldn't say that there's a point where, you have complete learning and, well, you're done or you've hit your limit. Instead, what happens is that the learning gets absorbed into your mind based on these generalized structures that we come up with, these things like eigenvectors. So let's have a look. Let's get a little bit more into detail here. When I said earlier, precision and recall, well, precision might be we only get what we want, which might exclude some of our target class. And recall is we get all of what we want, but we might include some that are not in our target class. So if I'm trying to be really precise, you say, went to the store yesterday. That's pretty vague. That could mean any store. So that's really high recall. It's just a store. Now, if I said, what store did you go to? Tesco or Waitrose? That's very precise. But the problem is it could be wrong, right? I said, no, I went to co-op. No, I went to the farmer's market. Uh, Once we make something very precise, we could miss our target. If we make something very vague, like recall, well, the store covers all of them. It covers Tesco and Carrefour and Sainsbury's and, Walmart and whatever. So it's very vague. It's recall. It covers all of them, but it doesn't get the target. So it's hard to get both the target and cover all the bases. So the autoencoder's dilemma is when to privilege precision and when to privilege recall. Now, it's not the same way that say, well, there is a right answer. The answer is whatever store you went to. That's true. That's an ontological question. But what's important here is not what store I went to, it's how can you know? How can you share meaning about that? How do we communicate meaning about what we know? That's an epistemic or epistemological question. And so think about how that dilemma operates in using two scenarios. So here's scenario number one. You have a cold. We say, go home. You might have COVID. Do you have COVID? Well, we don't know. I mean, ontologically, there is an answer. The answer is you either do have COVID or you don't. But epistemologically, what do we know? Well, we don't know. We don't know if you have COVID. We know you've got sniffles and other maybe symptoms that will be correlated with COVID. So what do? We use a recall strategy. We say, the target class has COVID, and we want everyone with COVID to socially distance So that means some people with COVID-like symptoms are also going to be asked to go home, even if they don't have COVID, because we like I said with recall, we might get all of what we want, but we might include some that are not in our target class. If we saw that over here on the diagram, recall here means that if we cut this way, are we going to get all the people that have a health issue, the red ones? But it doesn't mean are we only going to get them. It means are we going to get all of them? So recall down here is one score that we have. So actually our target class got all of them. But the problem was is it also got some that were not in the target class. We got some green ones up here. We got some red ones down here. That's a problem. So let's think about that again. This is a recall-based strategy. Maybe we want to be a bit preventative. And now here, let's think of the other side. When do we want precision? Well, imagine you have a suspect for a crime. And we say only convict beyond a reasonable doubt. Now that's a precision-based strategy, not recall. In this case, the target class is did the crime. And we only want to imprison those who are guilty of that crime. We don't want to imprison someone because they happen to be at the scene of the crime or they look kind of like the person. It's not like the COVID example. It's like if you got some sniffles, we're going to put you in that class. That's the you should go home and socially distance class. In the policing case, we don't say you look kind of like a criminal. We'll put you in the criminal class. We don't do that. That would be a problem. That would undermine people's rights, but it would also just, from a structural point of view, be a problem. Now we have an idea for this in policing that called Blackstone's ratio. And Blackstone, and this was in some legal texts, so like over 100 years ago, had said it's better to let 10 guilty people go free than it is to imprison one innocent person. So the idea is we got to have some tolerance and we got to figure out what that tolerance is. And Blackstone is saying the tolerance is we're going to tolerate some people out of, who might actually be criminals going free because the important thing is precision. We only imprison those who've done the crime. Blackstone's ratio is 10 to 1. Is that the right ratio? What if we say we never imprison someone unless we're absolutely sure that they committed the crime? Which absolute total precision. Well, the problem is that means we're going to get a lot more guilty people let free because they might not meet the standards of evidence of like absolute total 100%, not even beyond a reasonable doubt, absolutely incontrovertible evidence, right? That's a really strict test. And we could use that test, but it does mean that some people who are guilty will fail that test. So we have this tension, recall and precision. And this is a tension for meaning, because what we're talking about is how do we come to know whether you have COVID? How do we come to know whether you were guilty of a crime, whether you were or worth punishing? Now, whether people are worth punishing for crimes is a slightly different matter, but I hope that this communicates for the sake of the talk. So now how do we manage this? Well, the thing is we can't have a right answer. There's no perfect right answer. There's only sometimes we use some strategies, sometimes we use other strategies. And the strategies we use are context dependent. If we were able to know exactly if someone did a crime and then, like Pinocchio, their nose got long, that would be a very clear signal. It would be an unambiguous signal. Pinocchio lies, his nose gets longer. But we don't have those signals. We have data that's messy. And we still are asked who do we want to screen for blood pressure medication? We got to screen some people. So when are we going to say one or the other? But this doesn't just concern, blood pressure screening or like classification type stuff in that way. Again, it concerns all meaning. Now, unfortunately, I couldn't get the video working for this one, but I would encourage people to look this up online. This is from the planet Earth, and this bird here that shows the bird practicing his dance. It's a he, and he practices this dance. He does these spins, he does these flips and stuff, because he's supposed to attract a mate, and they're pretty gendered, sort of split. With this bird, I'm actually blanking on the name on this one, unfortunately, uh, but they're pretty split. The other bird is just kind of brown, unremarkable, uh, but she's there and she's looking for this dance. Now, but the important thing about this dance is that it's not scripted. It's not like she has a checklist with her. She doesn't go like, okay, he did the flip, great. Then he did the spin. Then he did the thing with the legs. Then he scooted around on the ground. Okay, perfect. All right, let's meet. Um, there's no formal checklist for these birds. These birds have to present this dance, and then the other bird will use an eigenvector like approach. She will appreciate the totality, the gist of this. She will say, well, his dancing's pretty good. It's good here. It's not good there. Is it good enough? If it's good enough, they're like, yeah, it's great. They'll mate. As it happens, unfortunately, in the image and or the video in Planet Earth, we discover that the other bird was not interested. This was this dance, whatever involved, it was not good enough. And the other bird has no real way to communicate that. It just they just basically either say, yeah, it's in or it's not in. Oh, yes, it's a bird of paradise. Sorry. Ah, merci. Yeah, of course. I don't know why I was blanking on that. Thank you. Yeah, so
No problem.
what they're not doing is like using a declarative checklist. What they are instead using is this autoencoder type thing where they can appreciate the general idea of what a good dance would be. So now this is a dilemma. We can't have both the bias and the variance. We can't, you know, optimize for precision and recall at the same time. So what do we do? Well, we solve this pragmatically. And that's also pragmatics from language, but we can think of pragmatics from pragmatism, and that's from Charles Sanders Peirce. I'm a huge fan of Charles Sanders Peirce's work, and would be happy to talk more about him in questions. But we can solve this pragmatically. So we can say, in what context was the statement said in order to guide us of the meaning of the statement? You know, when I say I went to the store yesterday to you, it's different than to someone else. I might say use different words with you. If we're talking about what's a friend, is this person a friend? That might be different if we're talking to just acquaintances. Yeah, you know, I'm friends with so and so. Let's see, who might I say I'm friends with that's not really accurate? Um, okay, someone might ask me if if I know anyone in human computer interaction. And then I would say, well, I'm friends with Ben Schneiderman. Now, Ben Schneiderman, if you have never encountered his work, he's a real important figure in human computer interaction. He, among the things that came up with is the link, as in the link that you press, it turns a different color, it's underlined, takes you to another site. Yeah, he invented that. It's kind of cool. Someone had to, and it was him. Now, I worked with people with Ben in different places in Microsoft Research, and I've had lots of I'd say lots. I've had a few conversations with Ben, maybe half a dozen, maybe 10 or more over the course of my career. Would I say he's my friend? Well, depends on the context. You know, if I'm talking to a close friend of his, I wouldn't say, "Oh, we're best friends," or like we're friends, because that would miscommunicate it. But if someone came to me as a student and said, I really admire the work that's happening in this domain. Do you know anyone who's doing work on this or who I can talk to? I would say, yeah, well, you know, friends with Ben Schneiderman. I'll send him an email and introduce you to him. And there it would work. That's working pragmatically. We're not saying there's a right answer to that question of friend. We're saying that here's how we resolve the bias variance trade-off in that context. Now, it turns out we can also build models that account for context. And those are transformer models. Unfortunately, we're not going to get too deep into the technologies of that. Unfortunately, we don't really have time for that, but we'll get in a little bit of it later on. But the idea is that a transformer model doesn't just treat a word as a single meaning direction. It accounts for all the different meanings of all the different words at the same time and transforms things together, transforms the whole matrix of words. There's a bunch of words and they have a bunch of numbers attached to them, and it transforms all of them together so that we learn, you know, you know, I related to went, related to store, related to yesterday, and maybe it's like because I went to get the stuff, and all of that is considered jointly by a transformer, which is why transformer models seem to be able to converse with us really successfully and even make sense. We might say they're able to generate meaning. And that's because they can understand words in context. It's not like a search engine or a kind of naive search engine. You type in the word dog and maybe it shows up the Wikipedia article and whatever. But if you say, tell me about dogs or which dogs you like or which dogs I would like, then a transformer can use all that extra information to give you a better discussion of dogs, or at least a more context appropriate discussion of dogs than you would just get on a generic Google. Now, the problem is what if we get this wrong? What if I make an inference that's inappropriate? Um, what if I make it hard to make a certain kind of inference? And that's where I describe this in terms of epistemic capture. See, the thing is when we get these eigenvectors, when we get like the gist of something, that's not getting all of it. That's getting a kind of simplified version of something that we're using to say, well, it's most of the way there. That's good enough, isn't it? Well, it is good enough for a lot of the times, but it might not be good enough for all of the time. Uh, we might be talking about a very conventional word. We might say, okay, what's one that comes to mind? Uh, so think of the word fish. So if I said, if I was playing with fish yesterday, what would you think? Would you be like, what? Why are you playing with fish? Did you like hold them? Did you move them around? And I'll say, no, 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 no. The fish is that's the nickname for my buddy. Yeah, we were playing video games together. You remember Fish, don't you? His name is like Joe Fish, but we just call him Fish, right? Oh, oh, that's what it means. So in that sense, we're using context, we're making assumptions, but what if I'm really credible and it's not like there's an easy right answer. What if I say something like is it here's a conversation I had recently. Um where I asked a large language model about male or games with male protagonists and like a female love interest. So we might call that straight. And I'd say this is where are there games with that in it? And of course there are, one would think. But I said, well, where's the AAA titles, the really big ones that have that in it in the last 7 years? And the model gave me some answers, and then we kind of went back and forth. But what if it ignored some games? What if it if what the thing was that online someone was saying there's no games with just like a guy who's got a love interest as a girl. It's all these sort of queer people out there now, and there's no games for people like me. I didn't believe that statement. I didn't think it was fair to say that. So I went and encouraged, or I went to searching and said, well, are there games with this sort of thing online? And it turns out there's actually not a lot of AAA titles that are heterosexual or heterosexually oriented now. Instead, there's a lot more titles that are either queer or you can choose your gender, or there's non-binary people involved now. It's really wonderful the ways in which people express themselves online, but the kind of like you know, guy has a love interest and he, defeats the dragon, gets the princess, that sort of trope narrative. It's not really, there's not a lot there. If I just read that online, I would go, yeah, there's not a lot of games out for people like me. That's a form of epistemic capture. It's a way of saying I'm restricting how we can make sense of this space. Models can also do that as well. They could be trained on the wrong data or limited data, or they may be trained on data where they prefer a meaning for how we would discuss politics. If we have a model that's trained in Russia, how would it describe the Ukraine Russia war? Well, it would the same as every other model would do. It would just take the data and put it together and make sense out of it and make this generalized sense from it. But when I ask it, it's going to have some sort of bias. It's going to steer its understanding in some way. And that might be different than my bias. And I might not even notice that because of the subtle ways in which models will explain things to people, but also the subtle ways that people exclude certain ideas because they say, well, everyone gets the general idea, everyone gets the gist of it. What they're doing is they're taking a strategy that says there's some ways of thinking of this that are just do not compute with our model. So the autoencoder's dilemma is related thus to things like censorship, but not censorship in a absolute sense, censorship in a soft way, where we say that only some kinds of meanings are available. Oh, before I go, here's a really tidy one on this. Don't worry, this one's longer than the encoder's dilemma, but that one's more colorful. Uh, yeah, here's a tidy one. I was asking, this was back in ChatGPT 3.5, trying to interrogate it to see when it would say, you should talk to your union. Now, we know that union membership is not anywhere near as high as it's been in earlier eras. That's especially the case in Britain and in the US. I know that union membership is still higher in France. And, but I ask, I have a problem at work. Who can I talk to? Does ChatGPT recommend talking to my union? Does it think to ask me, are you in a union? Does it ask whether there is a union? Well, no, it didn't until 4.0 or 4.0 or whatever. The 3.5 model, I really had to coax it with very specific details about the NHS, National Health Service, or me being a teacher or a professor before it started thinking about a union. And even then, I really had to coax it before it thought of that. The default thought was say, you should speak to your manager. But if your manager is the bully, then that's a problem. So you say, well, you should speak to HR. It assumes there's an HR. It's making assumptions about how to disambiguate this situation, which may or may not be the same as the assumptions that you need to disambiguate this situation. Because it's created this autoencoded, this generalized understanding, and it's working with that, which means sometimes it's going to miss the mark. It's either going to have too much variance. It's going to say, well, in this circumstance, you would do this and you would talk to this about this person. Sometimes it's going to have too much bias. It's going to be too general. It's going to say, talk to your boss. And that's not good enough. That's not specific enough. So when we resolve these dilemmas and try to preserve context, again, we're not thinking that there is a right answer. What we're asking is this contextually appropriate? Can we make information contextually appropriate? What happens when we don't? What happens when we can't? So that's the autoencoder's dilemma. How should we be really specific? Should we be really general? If we be really specific, we might miss the mark. If we be really general, we're too vague. It's not useful. But that's how we think about the world. It's how we come to understand the world. But then we have to speak in the world. And so if I have this generalized idea of, general, talk to your boss, or, when I go to the store, it's Tesco or whatever, you can have this general idea, but how do you express it? And how do you express it succinctly? Now, for the next slide, I need to contextualize this one. I think it's worth contextualizing, in keeping with the presentation. Uh, this is a flag from Reddit, from the site Queer Vexillology. Vexillology is the study of flags, and Queer Vexillology is a site where people put up flags related to queerness. And so you may know, or many people will remember the flag in the background. That's this the pride flag. It's 6 colors. It's all good. You'd have it in a store. It's like, oh, they're gay friendly, and that's great. I myself, I have, my sexuality is such that when I was younger, it was 20 years ago, 25 years ago, it was really meaningful to see a rainbow flag in a store. Um, and I'd say, oh, wow, this will be a place I could feel safe. This is a place that will not judge me, whatever. But what do we have now? Well, we have a pride flag, we have a progress pride flag, we have multiple versions of a progress pride flag. And so this here is meant to show the kind of extreme case of how we might resolve this with high variance. This is the encoder's dilemma to say, I don't want to just encode you as a queer person. I will accommodate your specific flavor of queerness. And when you do that, you end up with like an absolutely absurd number of flags. And some of them we recognize, some of them you might not. There's things for, well, there's trans people there. I see the bear flag over there, and a couple ones. There's a lesbian. There's a Achillean, which is I guess just for men, straight men, not straight men, but men who are into men, and so forth. The non-binary flag. But there's tons of these here, and I don't really know what they all mean. If someone was to fly a number of these flags out their window, I wouldn't have the first clue. I wouldn't know that they're part of the queer community. Wouldn't be able to tell if it was for a video game or a political campaign. The problem is I can't absorb all the information of all the flags. So when you communicate a sentiment, are you communicating something that's too general or too specific? The encoder's dilemma is, well, you could be more specific, but then look, you got like hundreds of flags you got to deal with. But you could be more general, but then that creates ambiguity. Maybe you want ambiguity, maybe you don't. And so, it's, the encoder's dilemma, how do we say what we mean? And here's an example. I know it's blurry. I really don't think it's worth trying to read all of the different flags there, but but we can say, the queer community provides us with a clear example of the encoding challenge. So is that the LGB community? Well, I would hope not. There are some people who will reframe it and say that I'm part of the LGBT community, and they will undermine or minimize, exclude trans people. Um, Traditionally, we would want to include trans people. I would myself personally absolutely think it's part of the queer community. But what about those who don't really fit a box? Well, we might say that they're just queer, and so we can have LGBTQ. What about other people? Well, we'll just put a plus at the end. And then the other people say, well, actually, some of us are really important, like intersex, asexual. So then you get LGBTQIA. And then you say, well, that's Western, that's cultural, that's, Eurocentric, we might say. So then we'll say, okay, well, we'll accommodate, something that's not Western or Western centric. So we might say two spirits. So this now, 2S LGBTQI plus is the formal term that is used by the Canadian government now for the LGBT community. Do we know what it means? Do people know what it means? Does it do, or will they say it's the alphabet soup, or it's just like it's some sort of United Colors of Benetton type thing? If anyone even knows that reference anymore. But the problem is that as the term expands, as it's trying to encode more in the term, you want to make sure that you get everything right. Well, the term becomes harder to infer, becomes harder to know that when I say LGBT and you say 2S LGBTQI plus, we're actually kind of really referring to the same thing, really. But we're not, because, well, this one's Western, this one isn't. And so thus the encoding problem never really goes away. Instead, it becomes that dilemma where, should we be more elaborate? Should we take more time to say more things? Or should we be more succinct, knowing that it's going to be more vague? And we don't have all day. We often we have trials and pressures. But also within here, when we encode things, we again have an issue of epistemic capture. What is meant by this? So this will get a bit spicy if you can bear with for the next minute or so. Where does BDSM fit in the Guide to Sexualities and Gender Identities? Now, the reason I say that is not a particular interest in BDSM myself, but of a historical recognition that there was a time when there was really just the pride flag, the bear flag, and the BDSM flag. The BDSM flag is like, it's got black and it's got blue, and I think there's a little heart on it. I can't really recall. You don't see it a lot lately. But that where there was a time when there was those were the queer bar flags. So how did that flag get forgotten? How did we redefine what the queer community was such that that was out and this was in? I mean, we could say for a number of other things. There's one in the down in the corner, we say not in the community and says maps, aka pedophiles. That's probably pretty easy to reconcile and for a lot of people and as a political community, uh, various people interested in young people, I guess, whatever. They tried to be in pride parades in the 70s and they were like kind of like, no, guys, no, we don't want to do this. But in a medical context, are they still, is that still a queer orientation or a non-typical sexual orientation? Well, it is, yes. Some would say it's a parasexuality. They'll define different words. But the point is that what we mean by sexuality itself is also when we're encoding that, are we talking about a sexuality that we want to support and think of as valuable, or one that we want in a taxonomic sense that is accurate? And this diagram, as elaborate as it is with omnisexual, pansexual, abrosexual, polysexual, and bisexual, um, all under the guise of multisexual, is in. But bestiality, pedophilia, whatever stuff is out. And yeah, again, from a political context, makes sense. From a medical one, not as accurate. Doesn't work in the same way. But the encoding is like, how do we make this succinct? And so that I say said from machine learning, we talk about the curse of dimensionality. And so here's kind of a rushed version of how that plays out. So if I say, are you gay or are you straight? And people go, oh, I guess I'm gay. You know, there was your two choices. And people say, no, people can be bi as well. And then the straight person goes, well, I'm mainly straight, but I mean, I've had my experiences or whatever. And so they actually put themselves, now that you have a third one, they put themselves in that category. And then the gay person learns what pan means and goes, well, I'm pan. And then someone learns what omni means and they go, well, actually, I'm not bi. I think omni is probably the better word for me. And all of a sudden, they're getting what we're doing is we're adding dimensions that make it more granular for each person. But unfortunately, that means it's harder for other people to manage what information is being communicated. If I said I am pan versus omni, would you know what I mean? I'm not sure I remember what it is, in fact. Um, it says here that omni is someone who is attracted to genders, but they have a preference. And pan is someone who's attracted to all genders without a preference. It's a really subtle distinction. Do we need that distinction? Well, it's not a normative question. The question is what happens when we use that distinction? When we use it, do we end up conveying enough information or do we make things more noisy? Because we're adding new columns to our data, but that makes it harder for us to know what each column represents. We can also see this in an example here. This is from uh, some lecture notes of mine on naive Bayes clustering. And so we might say the categorical syllogisms are logical ways in which we arrange ideas. And here's two categorical syllogisms, one of which is true and one of which is not true. If we say all ducks quack, and this fella quacks, therefore this fella is a duck. We could also say all ducks quack, this one is a duck, therefore this one quacks. One of these is true, one of them is not true. The top one's false. We could, in theory, have something that also quacks, but it's not a duck. I could quack. That doesn't make me a duck. But in this case, if we say all ducks quack, and this one is a duck, then therefore this one will quack because it's entailed from being a duck. So these structures we use in order to predict things, but in real life, we don't have all of the data. So we might train on some data. We say we have a duck. It walks, it quacks, it has feathers, and it's edible. Whether you eat it or not, maybe about your diet, but I know that people do eat ducks. So we could say it's edible. Now we have a robot which also and it quacks as well because it's like programmed and it can make sounds, so it makes a quack sound. But it has metal, or it's made of metal, and it is not edible. I would really discourage you from eating robots. Okay, so then we can make a prediction here, and we can say we have an object. Well, it walks, it clucks, it has feathers, and it's edible. We would say, well, which it is? It's more likely to be a duck. But that doesn't mean it's a duck. It means that what we're doing is we're saying it's more likely to be a duck, and that would be our prediction. But of course, it's a chicken, you know, and that's an ontological statement that it's a chicken. The problem is that we didn't have enough categories to identify the difference between a chicken and a duck. We would need more categories for that. But if we have too many categories, then we don't learn what a duck is. Imagine we're not talking about a chicken, but we're talking about some sort of Chinese heirloom chicken. That's a very specific chicken. Do we have all the rows that can differentiate it from another chicken? Do we need to? That's the encoding dilemma. When are these things important to differentiate in one way? Again, we might say it's not about correctness in meaning. We're not trying to say this is what's the right meaning. We're trying to think about how do we convey information from one place to another. Under what conditions would someone declare being gay versus bi versus pan versus omni, to go back to our earlier one? Well, if it may make a difference if you're thinking about marriage rights or property rights, if you're talking to people online, if you're talking to your family, it could make a difference. See here, in some contexts, people seek granularity. Would say like, well, I'm only into bears. It was like, that's kind of big, beefy, overweight guys, whatever. When would one say that? When would that be contextually appropriate? There are places where it would be. Maybe you're saying, oh, I have a friend who's gay. You'd love him. Go meet him. And then I'd say, oh, I'm only into bears. And we go, oh, okay. So, right. Maybe that would be an appropriate case. When would I say I'm gay? When would I not say that? When would I say my partner is a bear? Each one of these are different levels of specificity. And we often can feel that socially when we say, well, that's too much information. What we're doing is we're being too specific about the information for the context. But unfortunately, there's no out of context statement that will cover all of these things. If we're really specific on all of this, we may be giving too much information for the context. And it's not about thus being correct. It's about being what's accurate in a practical sense for that meaning. Now let's think about this with social science. We're winding this down. We're near the end, and I'm going to show a little bit of complicated machine learning stuff at the end of this. But I want to nail this particular concept with looping it right back to networks and those ideas of friends and what is a friend. Well, we've actually been thinking about that a lot in network analysis. And it makes a difference if you're studying things online, if you're trying to study who is talking to who, what they mean, how they mean by what they say. Well, when we've been asking people about what we call the core discussion network, those are the people that are really important to you, the ones that you talk to about stuff, maybe get some, good advice about the world. And we we've decided, a committee, I guess, has selected the question, with whom did you discuss important matters? Now, that in itself is already contentious. It turns out, if you look in the history of this, there was a bit of a debate about whether it should be important matters or important personal matters. So when I say, with whom do you discuss important matters? You say, well, like my taxes? Should I put my accountant down? And they're like, no, not your accountant. No, we don't talk about that. I mean, yeah, taxes are important or whatever, but I mean, like, your mom. Who's important to you? Because oh, is the person that's important, not the matter? Oh, right. So we have construct challenges with this stuff. And this led to my favorite title in all of science papers. There's some good ones out there, but I think this one's my favorite. Cloning headless frogs and other important matters, conversation topics and network structure. And so Peter Behrman is a really phenomenal sociologist. He's done all kinds of work on networks, and he is doing work on ICTs and social media now, but he's really runs the gamut. So he did this paper with Paolo Parigi. Paolo's also a really accomplished social scientist, and they asked people, okay, so you know who's with whom do you discuss important matters? And people say, well, my mom, Joe, and David. I'm like, okay, very good. Why'd you say them? Well, it's important. What's an important matter to you? Well, there's really, there's things that are happening in the world that I'm not really comfortable with. There's like genetic testing and people like cloning these frogs. I heard that they're like cloning frogs without heads now. To me, I'm weirded out by that. And so, yeah, that's the sort of stuff I'd talk about with Joe. Okay, so in that sense, it's not actually cloning headless frogs. It's more kind of how people are concerned about science, science interpretations, medical experimentation, ethics. But it's hard for people to talk about that generalized vector. They're not going to say, I'm going to give you the eigenvector of my moral orientation. What they're going to do is they're going to talk about, locate things on that vector. They're going to say, headless frogs or microplastics or climate change, and it might not be just about climate change, or it might not just be about like microplastics in the brain. It might be microplastic broadly, but people don't give you the eigenvector. What they give you is some words that they hope you will disambiguate to know what they mean. And when we miss the mark, then we don't get the right information. We don't get the right kind of network. This is related to construct validity in sociometric work. How do we create an appropriate construct? But I don't want to just boil it down to construct validity, because construct validity implies that there is a real concept out there that if we just ask the right question, we'll get that construct. And what I want to suggest is that there may not be a right construct out there, because the constructs, have to deal with this bias variance trade-off. Some constructs can be too specific, some too general, but there's never really a right answer. The answer depends on the context. So this is what we'd call the curse of dimensionality. How many dimensions do we need in order to cover all of our stuff? But knowing that if we get more dimensions, things get more vague. And so how do we resolve this? Well, we contextualize things, and we used to do this using a fixed encoding. Uh, and a fixed encoding is something like sentiment analysis. We have the words happy and sad, and we give them a +1 and a -1, and we sum up all the words and say, well, that's the sentiment score. And that's a total sledgehammer to this. It's really superficial. So then after sentiment analysis, we used things like word to vec. And word to vec is really cool in some ways and can give you these sort of mappings, which I'll show in a minute, like man is to woman as king is to queen. Now, I don't even love that analogy, but it is the popular one that's out in the field. Uh, but the thing is that that works because it's assuming the main understanding of man and the main understanding of woman and the main understanding of king and queen. So let's see, actually, I'm going to skip the next slide and scoot right over to that. So this is what it looks like in vector space. What it looks like is you take man, and if or if you take king and you subtract man, then you add queen, you'll get to here, woman. Or if you take king, subtract man, and add woman, then you should get to a thing that will be the queen. Like this is how you will produce those analogies. Now, analogies aren't perfect. This is what it looks like in a recent paper. As you see from the URL down there is where they link to the paper. It's from Edinburgh. They're not the only ones doing work on this. Well, maybe man, woman, king, queen leads to this space up here where queen is. But if you keep going, it also leads to prince or crown or princess or lord. So it could lead to all kinds of other words. But all of them here are about royalty, aren't they? What if I said Robert Plant is to Led Zeppelin as Freddie Mercury is to blank? Now, Led Zeppelin's a band. The reason I use them is because they're also from the 70s. They're also arena rock. They also have a lead singer. Yeah, that sort of thing. But the word queen in this case does not mean a monarch. That doesn't mean a person with a crown who's female identified. It means the band with Freddie Mercury. Those meanings are all kind of squished together in the models. They have to be because we need to understand the context of the word in order to make sense of it. So how do we do that? Well, transformers do that by taking a thing called a token embedding matrix. They have a dimension of words, generally a few hundred dimensions, 768, 1024, one of those nice, powers of two numbers. And it has one of those for each word. And that becomes a matrix of words. And then what it does is it takes that matrix, it weights it in some way, and then it starts combining them together. And this is the formula for how they're combined together. Now, we can't go into the details of that formula here, unfortunately. But the reason that they do it is because all these words are all mixed together. Um, and this helps us think about queen in the context of the other words like Freddie Mercury or the other words like royalty, princess, monarch, whatever. So that's why transformers are really useful in this space, but it does not mean that they can come up with the right answer. It means that they're only as good as their weights, what perspectives they already have, and your ability to activate that through context. Now, winding this down, I will say it's pretty neat to have discovered that we can actually find these man, woman, king, queen parallelograms inside of a model now, inside of a large language model. They're not there right away. If you do it right away, you get something like, this right here, this sort of weird triangle thing, where Austria to Vienna is is not the same as Switzerland to Bern. It should be, but what happens is Austria to Vienna is the same as Switzerland to, and you see how Switzerland's kind of going off in a different direction. What we need is for them to say this is to this as this is to this. Kind of nice parallelogram, they say. That's the analogy. This is parallel to this. Well, they've been able to find ways to look in these models, and this is from Lee et al. I love this paper. This is the geometry of concepts, using a thing called linear discriminant analysis, which allows us to understand what concepts mean in a model. But the thing is, it's not like the concepts mean something eternally. The concepts only mean this because we've preloaded the context and then we look to see for stuff. So that's what this the paper is about. It's showing how we can like reveal these meaning structures inside of models. But in order to do it, you can't use models like this. You can only analyze them like that. The model you use still has everything all kind of bound up together, and what we would say is all entangled. And because it's entangled, all those meanings are all along for the ride. And what we cannot do is say get the right meaning. We can only trade off bias and variance, or precision and recall. Precision and recall are like the epistemological versions, bias variance are the ontological versions, but they pretty much refer to the same thing. All right, so almost near the end, second last slide. So let's revisit the autoencoder's dilemma. So we can say, given pressure to be succinct, can we say what we mean sufficiently? When I say I went to the store, is that succinct enough? When I use a particular sexuality label, is that too succinct? Does it convey what it needs to? Can the listener de-equivocate the meaning of a word from context? For humans, that context might be the environment or the history. For a model, it's the other words that come in and how they refract across the learned weights in the model. So we need to ask, what do we do with context? Who shapes the context? Who determines what meanings are available? So now what am I doing with this sort of work other than this? Well, this is theory. I've submitted the autoencoder's dilemma as a paper. I mean, hopefully it'll do okay. We'll find out. Maybe not. But I really like it actually. In practice, I'm doing some work in what we call computational social science about how we disambiguate empathy as a concept. It turns out that different forms of empathy are more or less successful in different online sites. Now, this paper is an R&R. It will be for Computer and Human Interaction, or the Conference on Human Factors. And so stay tuned if you see this paper, released in a few months. It's available, but I would actually, this one I prefer not to share because I'm not the lead author. But what we did is we trained a model to look for different kinds of empathy, and we found that different subreddits or different forums on Stack Exchange, different kinds of empathy were successful. What people often say as, well, we just want to make the model more empathetic. Well, that doesn't work if you if your model if your concept is overloaded. If we don't know what you mean by empathy, do we mean you're taking my perspective? Do we mean that you are offering help? Do we mean that you are supporting me? We might say this is cognitive empathy, or affective empathy, or theory of mind. They're all kind of bound up together. But when we've been training models and saying, let's make the model more empathetic, we number one assume that it doesn't matter based on context, which is bad. And we're also assuming that there's only one kind of empathy, which is not true. They're not even very well correlated as it happens. Another thing I'm doing in user experience is how can we fix meanings in context with LLMs? So I'm working with a major tax corporation or a tax organization, and who works with tax organizations? But me, apparently, and an artificial intelligence company. I will be disclosing all of that once contracts are signed, but and they're going good. But gonna have to keep it ambiguous for now. Why taxes though? Well, everyone looks at health in large language models. Does it give you the right health information? Well, for health, we might be able to say that there is a right context if we say what makes people healthier. Maybe not, but we can't say that at all with taxes. There's different words for different countries, different jurisdictions, different times, where there is no like right meaning for thing in terms of tax. There's only jurisdictions, only places where some policies apply or don't. So how does the model know when to apply the policy and when not? And also, I'm also looking at this from like the deep math perspective. Which concepts are more or less entangled? How does it mean to say a model or a concept is more entangled? Well, that involves things like steering vectors. And if we're a bit dull on the questions, I can show you some steering vectors and see what it means to take a model and make it more dog-like, or make it more like it's yelling at you. You can now tune those, but you can't push it too far or the model starts breaking down. So that's sort of interesting, a way that we've learned that these concepts are entangled. You can't just maximize the empathy vector without mucking up other things in the model. This trade-off is non-negotiable. We always have this trade-off. So here's it is, the summary. Well, the autoencoder's dilemma is when to privilege precision and when to privilege recall. When do we want all the things? When do we want to be exact? And how do we kind of figure out which is which? The encoder's dilemma is, given the pressure to be succinct, can we say what we mean sufficiently? So the first one is about more like how do we perceive, and the second one is how do we relay or communicate what we've perceived. But in both cases, we have kind of a similar trade-off, and there is no right answer. We won't find a right answer because we've proven that there's no right answer, technically, mathematically, and here mostly anecdotally. And the stakes for this are pretty high, in fact. We might say, what general representation is available? To whom? What happens when we miss a line, but one interpretation is dominant? When ChatGPT says, talk to your HR manager, but I think, well, maybe you should talk to your union. That's the stakes involved in this. How do we determine which of those meanings is just subtly nudged out of our worldview so that we're not even talking about it? And then what tools are available as concepts in a context? When can I say something like bears or omnisexual or whatever? In some contexts, people won't know what I'm talking about. It won't work for me to say that. And in other contexts, it will. But who determines what's legitimate or not legitimate in those contexts? We can ask that question in many ways, but I'm asking it here in terms of these two trade offs. And if those are our trade offs, but we have to communicate, we have to say something, well, who is the one that's determining what's okay and what's not? So that's it. You know what? I didn't put a thank you slide in this one. I normally do, but let me just thank you for the opportunity to share that. I hope it was somewhat clear, and if it generates discussions, I would love to hear from the audience about that.
Thank you very much, Bernie, for this brilliant and fascinating presentation about the issue of finding a good balance between recall and precision. You have presented powerful concepts that help us understand how we can have access to meaning, such as eigenvectors, equivocation, for instance. And you also gave us several concrete examples to illustrate these concepts. And these examples, according to me, were very relevant. So thank you very much again. And I'm sure there will be a lot of questions. We approximately have 15 minutes for questions. Who wants to start with a question? You can either type your question in the chat or raise your hand.
So if I can give another concrete example to warm people up, here's something that I think it's been a bit of a problem uh, when we do this the wrong way. So look at these blobs here. This right here is blog traffic, and it's from 2004 in America on the presidential election. People talked about it before the election. It's called Divided They Blog, and the researchers went and they labeled all of the blogs as either left wing or right wing, and then they show this. And they say, look, the left wing and the right wing are so split, they're polarized, but they're also constructing this as left wing or right wing in this way because maybe some are in the middle. What does it mean to be in the middle? And if you don't have the language, if you're not given the opportunity to encode with higher variance, then you just don't get to see the variance. We don't get to see which ones were labeled as maybe left, maybe right. Or we don't get to see that on the left, there may be multiple different kinds of left because we've made a choice to simplify it to this left right pole. And then we see the world in terms of that left right pole. Actually, this one right here is from a really good paper in Science Communication by Brooke Foucault Wells. Hopefully, this is the right one. Yeah. If you see this, this right here is a wonderful paper called Visualizing Computational Social Science by Brooke Foucault Wells and Isabelle Murray. And this talks about what happened when we just reduce it, and they refer to it correctly as a complex image. It has many layers to it, but it gets flattened into like, ooh, networks can show us that everyone is polarized. And that message, the meaning in that message, what I'm trying to help us think about is what's lost when we make these simple statements. What ability for us to navigate politics is lost when you label your data. If you're looking at data online, is that labeling accurate? And is accurate what you want? Maybe precision is what you want, or maybe recall. Maybe you want to say, I only want people who are far right. Or maybe you want to say, I want everyone who's got an opinion that's kind of anti-feminist, whether or not they're like incels and they say, oh, I hate women and blah blah blah, or whether they're more just like um, I don't know what would be the term. Girls don't get us. Why can't we just go out and play sports and something like that? Well, precision and recall. affects every decision we make about how we label the data that we're using, and thus how we make claims about that data when we're done.
Thank you very much for this new illustration.
Oh, I got tons of them.
Who will start with a question?
Well, to the person who said thank you, well, you're very welcome. Thank you, Karen. Uh, but for the
I will
rest of
start
you,
with a question. How do you think, how could you imagine to find actually the right way to find the balance between precision on the one hand and, of course,
recall on the other. Yeah.
recall on the other hand, exactly. So
Well, I think it we it is important for us to consider iteration in a system. Now, Peirce referred to this, Charles Sanders Peirce, in terms of infinite semiosis, how the things that I say, you interpret. They become interpretants. They become things that are kind of like the meanings based on what's in your head. And then you talk back to me and they become things in my head. And this process is always going on, it never stops. So, what we want is to think about the trajectory of meaning, the flow of meaning. If I reduce things and make them too simple, how will meaning flow? Will it flow productively because we now know who the players are? And it can. That's what voting does. We have many opinions on many kind of issues. We have many political parties that we can vote for, but they don't just overlap with our positions. So we say, well, I think these people are close enough to my values. I will vote for them, and then they get in power, and then they don't do a very good job. And you're like, I thought that I was aligned with them, but I'm not aligned with them. They don't actually represent my opinion. I see that now, and you change your vote. And so the same thing in all of these spaces. Well, if we make recall, if it's too far on the recall side, maybe we're imprisoning people that we shouldn't. That's an iterative thing. We learn that we release people from prison that shouldn't be in there. Governments pay lots of money and say you were falsely imprisoned or whatever. We use DNA evidence or so forth. So it's this thing is if we overcorrect one way or the other, there will be noise in the system. It'll either be equivocation noise because we don't know what it means, or it'll be channel noise because we don't know how to receive it and interpret it. Who bears the brunt of that noise? That's the question we ask to resolve this. If I say that back to the queer community, people I know and love dearly, I mean, married to a man myself, uh, when we're talking about rights for people, do we, what rights do we afford people based on their sexual and gender orientation? We might say, well, you have the right to be with whoever you want. And we say, okay, well, I'll be with a 15-year-old. And they go, well, no, 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 we did not mean that. And then we go, okay, understood. I mean, it's not for me. But the point is that we will find ways to correct. Somebody is going to have some noise. So if I say, well, then I'll just be with whoever I want. I'll be with someone who's in a vegetative state. Well, that's going to lead to some noise, some problems. Maybe that's not going to work. That's not consensual. That's problematic. But there's other places where this happens. Marginal cultures. When you have a marginal culture or a low resource language, if you don't train on that language and the people don't have anyone to communicate with that language, and they go, well, you just chat with ChatGPT. Well, I can't chat with it in my language. So therefore, I have to give a more noisy opinion. Uh, that I'm the one internalizing what we would say is the entropy. When we say that AI is going to be great for the world, and we really mean great for shareholders, that means non-shareholders are going to internalize the entropy. They're going to be the ones to have to deal with all of the bad parts of it. In all of these cases, when we overcorrect or undercorrect, we're going to create some uncertainty, and someone's going to have to deal with that uncertainty. If we say everyone is male or female, that trans is not a well, it's not like a real gender. They're not really women or men. Uh, then that means a trans person is now going to have to internalize that entropy. Their opinions, their life has been invalidated. If we say, well, no, trans people are, if a trans woman is a real woman, then the person who goes, I don't think trans women are real women, they're going to have to deal with the entropy. They're going to have to be the ones to manage the uncertainty. They're going to have to say, oh, I thought women meant this and men meant this. Someone is going to have to internalize that entropy. And if they can process it, then we can converge. If they can't process it, then they diverge. And so then you get multiple epistemic communities. And that's where we are now, unfortunately. We're in a place where we've offloaded the entropy onto different people, and now they just don't want to talk to us. And so we have groups of people who are mutually unintelligible. We have people saying, I can't imagine how you voted for Trump. Are you a fascist? And the person goes, no, I think Trump did a good job. Are you are you a communist? It's like, no. And people become mutually unintelligible to each other when we offload this overcorrection or undercorrection. What we want to do is minimize how much we have to offload, how much we have to, or offload it onto the right people or the appropriate people, the ones who we think it should be offloaded on. But yeah, when we're trying to, if we say we don't know if you have COVID, go home. Yeah, we've offloaded the entropy onto you, but that's okay because then you can go and take a COVID test. But if we do it the other way and say, unless you absolutely have a COVID test, you have to come into the office, then the office is going to have to deal with the uncertainty. And then we're going to have people around the office who might have COVID and spread it. So we need to look at who is making the world more certain in what way. And if they're doing that, somebody is dealing with uncertainty in their world as a consequence. Who is that? Is it just the marginal people? Is it just poor people or queer people? And how can we make sure that everyone bears a little bit of this uncertainty so it's not like just powerful people who get to say what is and isn't? This is for citizens, not for immigrants. That's a kind of a powerful exclusionary thing. And instead say, maybe immigrants shouldn't be treated like garbage. Maybe their problems are a little bit our problems as well. And if we ignore them, well, then we can ignore their problems. But that doesn't make the problems go away. It just means that we've offloaded the uncertainty of this semantic ambiguity. And we shouldn't offload that uncertainty. We should distribute it fairly so that everyone is a little uncertain, maybe, but that we're converging on some meaning together.
Thank you. I think that we have run out of time, so I will conclude the session. Once again, I want to thank you very much for your presentation today. It's always a pleasure to have you in this seminar. Thank you,
Thank you.
Professor Bernie Hogan. Thank you, Bernie. Once again, I will tell you some information about the next session. The next session of the seminar will take place on the 20th of March from 4 p.m. French time with Anna Terzi, a PhD student from the University of Stockholm. And this session will adopt a hybrid mode with an on-site session in Aix-en-Provence, which will also be available online with Zoom. Thank you so much to everyone and see you soon. Have a good night.
You too. Au revoir. Bye-bye.
Thank you.